The second circular case study of ICEBERG project aims to demonstrate circular cement-based products in Turkey. This work package was led by Beşiktaş with the participation of Hacettepe University, Simsa, Tepe Key Aerogel, and Sericat. The main objectives were to develop a novel eco-hybrid cement, ultra-lightweight non-structural concrete wall elements and green wood chip concrete panels, and prefabricated recycled concrete structural elements. First, a 50-year-old building in Ankara, Turkey, was chosen for selective demolition. A digital model was prepared to help audit the demolition work. The light demolition activities such as doors removal, windows removal, floorboards removal, and other items removal were the first stage. For the heavy demolition work, the roof parts and any other steel elements were demounted first. Then a long-reach excavator was used to complete the demolition. The sorted concrete wastes were crushed and sieved to be used in structural elements. Eco-hybrid cement was produced by Simsa. Construction activities were conducted in the civil engineering department at Hacettepe University. At the beginning, the steel reinforcements were prepared and special steel molds were assembled to be used for the concrete elements. These molds were modified to cast structural elements to be used in a one-story building. Then, a mobile concrete mixing truck was used in the mixing and casting of structural elements. Materials such as eco-hybrid cement, recycled aggregate, water and plasticizer used in concrete production were loaded and mixed by this truck. Finally, the concrete developed entirely from eco-hybrid cement and recycled aggregate was poured into the molds. The casting work was performed on different steps according to the type of the elements. In some elements, insulation plates were placed to increase the energy performance of the building. Approximately 90% of the concrete consists of end-of-life building materials. The concrete elements were removed from the molds after 3 days of moist curing. Different types of structural elements such as shear walls, foundations, slabs, and roofs were cast onto this project. With the help of a mobile crane, the mounting process started with the foundations, with a U-shaped channel on the inside that allows for the walls to be inserted and fixed easily. After all the foundations were connected, the walls were inserted, then slabs were fitted, and finally, the roofs were mounted. This assembly work took around 3 days in total, with all the interruptions. It should be noted that no extra mortar was used to fix the elements, which allows the building to be dismounted easily and transported to other locations. The recycled wood chips were treated with alkali to produce green wood chip concrete panels on an industrial scale by Tepe. The treated materials were layered in the form of boards, then cut and shipped to the construction site. For further field applications, the steel molds were transported to Malaysia, one of the major cities affected by the last earthquake. Recycled building materials were used to manufacture 2 buildings until now. The outputs of this work package attracted many local and foreign parts. One of them was Prince Edward, Duke of Edinburgh, who showed a lot of interest in this innovative work. The pilot production of the circular ceramics took place at Karaben's facilities, one of the industrial partners of the project. The objective of this case study was to manufacture ceramic tiles using a large amount of recycled materials obtained from the demolition of buildings, above 50% by weight. The first stage starts from the atomized powder with a new circular composition and consists of pressing and drying the ceramic body. The ceramic tiles are formed by pressing. Forming takes place by mechanically compressing the paste in the die and is one of the most cost-efficient forming methods for making ceramic ware with a regular geometry. The quality of the final fired tile will largely depend on the characteristics developed at this stage. Some are also crucial during the manufacturing process, such as the bulk density that can guarantee the necessary mechanical strength. Drying is also essential for subsequent stages. For this reason, moisture is reduced from around 6% to less than 0.5%. Glazing is done to provide the fired product with a series of technical and aesthetical properties such as impermeability, cleanability, gloss, color, surface texture, and chemical and mechanical resistance. The glaze layer can reach a thickness between 75 and 500 microns. Currently, ceramic tiles are mainly decorated using inkjet printing technology. Printing is conducted without the need to hold the piece and without making contact with it, thus allowing for complete decoration of the piece, including those with reliefs and rounded edges. Automatic laser-guided vehicles store the parts in an intermediate buffer until they're driven to the firing stage. In kilns over 100 meters long, the tiles undergo a thermal cycle, which initiates a sequence of reactions within the material, leading to modifications in the microstructure and conferring the final properties. For the circular ceramics, the cycle had a maximum temperature of 1110 degrees Celsius and lasted for 39 minutes. The perfect realization of the lateral rectification and chamfering of the tile sides allows perfectly 90-degree square corners with remarkable quality finishing. Grinding is the process used for removing material in the edge of the pieces by means of abrasive particles. In order to assure an exact size for the tiles, the ceramic tile manufacturing process ends with sorting and packing. The result for the circular tiles was a controlled product in terms of dimensional regularity, surface appearance, and mechanical and chemical characteristics ready for installation. A three-story office building located at Loughborough University campus in the East Midlands, United Kingdom, was demolished in June 2023. Plasterboards were located in walls and ceilings, and the pre-demolition audit and BIM-aided smart pre-demolition tool estimated that the total amount of recoverable plasterboards would be 5.1 tons. Plasterboards were dismantled using a crowbar and segregated in a dedicated skip. The skip with demolition plasterboard waste was transported to the recycling site of Enver. Demolition plasterboard waste was stored in a dedicated silo at Enver recycling site. This demolition plasterboard waste was moved to the mechanical sorting plant. The material passed under the primary magnetic separator to remove ferrous metals such as nails and screws. Afterwards, non-ferrous contaminants such as paper and plastics were removed manually by operators wearing personal protective equipment. The collected plasterboard fragments were moved to a dedicated silo at Enver recycling site for storage. The plasterboard fragments were ground to produce a gypsum powder with particles less than 2 mm in size. The gypsum powder was stored in bags and moved in a lorry to the acid-leaching gypsum purification plant at Enver recycling site. Intermediate bulk containers of 1,000 liters capacity and 96% sulfuric acid were used to prepare the required 5.39 weight percent sulfuric acid solution for the acid leaching purification process. This diluted solution was added to the agitated batch reactor of 8 tons capacity embedded in a steel framework. The purified gypsum was mixed with commercial stucco and reclaimed gypsum to produce a purified gypsum blend with 35% recycled content and 25% water content. This purified gypsum blend was then placed in trays and dried in a static oven dryer at 50 degrees Celsius for 48 hours to avoid modification of the chemical and physical properties of gypsum.